So our next contribution is one of my current colleagues. We both work at Surrey Satellite Technology down in Guildford. Andrew Cawthorne is our lead technologist on Earth observation, and that's the subject that he's going to be talking about now. Andrew, over to you.
Thank
you.
So I'm one of those people, when I'm flying somewhere, I'm glued to the window because I love looking down on the Earth. And I have to admit that my favorite is the mountains, but whatever it is, whether it's fields or cities or islands, I'm there because I love that variety, the infinite variety of our planet. I've heard astronauts say the same thing, and you quite often see pictures that the astronauts have taken from the space station. And whilst I would love to experience it the way that they have, I have to make do with the next best thing, which is using satellites to look down on the Earth for me. Now, this is more formally known as Earth observation, and as Stuart indicated, my job is all about Earth observation. I run the Earth observation business for Surrey Satellite Technology. What I'm going to say is the best small satellite builder in the world, but you might expect me to be slightly biased. Whilst I could spend probably hours and hours poring over the thousands of images that we take every day, unfortunately I don't get to do that, but I do spend a lot of time thinking about how you go about taking these images, and also why you would want to. Because actually, when it comes to it, taking images from space is a lot more complicated than looking out of the window of a plane. So we heard already some of the previous speakers talking about orbits. Before we get into the nitty-gritty of Earth observation, I want to talk a little bit more about orbits. I also want to talk about the basic idea of Earth observation, because looking at something from space is in principle the same as it is from looking at something on the ground. If I want to look at something that's a long way away, I need a telescope. If I want to look at something that's a really long way away, I need an even bigger telescope. If I want to take a picture of something, then I need a camera. And if I want to take a picture of something that's a long way away, I stick the camera to the back of the telescope. It's quite simple. The same applies in space as it does here on the ground, only I'm a lot further away. So I have to now figure out whereabouts I want to put that camera attached to the telescope in orbit. And that's where the orbits come in. If I start off over the equator and I launch my satellite going east or west, then what's going to happen is that the satellite is going to fly around above the equator. But that's all it's going to see. You can't see the rest of the world. You can see that the Earth is turning underneath, but the only thing that the satellite is going to see is what's underneath the equator as it's flying around. If I take it, choose to launch it into a different direction, so let's say I launch it north, then the satellite will fly up over the pole and back down the other side again. So in this way, I get to see a lot more of the Earth because the Earth is turning underneath as the satellite is flying around. And of course, there are an infinite number of variations in between, whether I launch choosing exactly the direction that I want to go in. So I have to figure out which way I want to do it, and I have to figure out exactly how far away I want to put the satellite. If I put the satellite very far away, then I have to have a really big telescope. And it also is really hard to get it there, because getting something, as we heard from Nigel, the further away we've got to get it, the harder it is to get it there. Conversely, if I have it really close to the Earth, it's very easy to get there. Well, not very easy. Easier to get it there. But now I have to contend with the things like the atmosphere, because whilst the atmosphere does thin out, it is still present. And if I'm too close to the Earth, it won't take long before it spirals back in and crashes to the Earth. I've also got to think about the fact that, well, if it's a long way away, I can see a lot of the Earth at the same time. But if it's much closer together, then my field of view is a lot more limited. So somewhere there's a sweet spot there. For Earth observation, that sweet spot is around about 500 to 700 kilometers away. This is in a region of space called low Earth orbit, or LEO, as you might hear it being called. And in that region, we are traveling, you have to be traveling at about 7.5 kilometers per second. So some of the previous speakers mentioned there's a range of speeds that you have to be traveling at, and that determines which kind of orbit you're in. For low Earth orbit, we're traveling about 7.5 kilometers per second. So that introduces some challenges when it comes to imaging the Earth. If you think about the fact that the satellite is flying past at 7.5 kilometers per second, you have to get your timing right. Because if you take your picture at the wrong time, you don't have to be out by very much. You're not going to hit the thing that you're trying to take a picture of. You're going to hit something else altogether. If I was trying to take a picture of this building and I missed by a second, or even I just didn't quite know where I was accurately enough to a second, then when I do take a picture, I'm not taking a picture here at all. I'm down in Wimbledon or somewhere. So it's really quite important to know exactly what the timing is. I also need to choose the direction that I'm going to be traveling in. And for Earth observation, we typically choose sun-synchronous orbits. Now, sun-synchronous orbit is almost like a polar orbit. You can see it's traveling more or less up through the Earth around the poles. But it's at exactly the right angle so that the sun stays in the same position relative to the orbit all of the time. So the picture on the right there, you can see, this is looking at the Earth from the top. The sun is down here on the ground in this picture. And as the Earth is turning, that orbit that the satellite is going round in stays in the same place relative to the sun. What that means is that it's always the same time of day on the ground underneath the satellite, which makes taking the images a lot easier. Now, of course, because the Earth is turning underneath, it's not the same place under the ground, it's just the same time. So in the end, after the satellite has been going around for a long enough period of time, then I get to have seen everywhere on the world. At the poles, it might be quite quick because I'm going to go around in orbit every 90 minutes or so. At the equator, it will take a couple of days probably. But the point is that I will get to see everywhere at the same point, and the time will always be the same too. So what else matters in designing an Earth observation satellite particularly? Sean already mentioned a number of the things that we have to think about for satellites in general. And I'm not going to talk about a lot of these things, but one thing is particularly interesting for Earth observation, and that's wobble. This is an image taken from a satellite that was wobbling. Now, it's not that useful as images go. This is actually an airport. Those things there are runways, maybe, just about, and some buildings. But what's quite amazing, really, is that this satellite was wobbling. The camera was wobbling by a few arc seconds. What that means is the camera was not staying still by about 1/1000th of a degree. If you were looking at it, you wouldn't even be able to see that it was moving, and yet it turns what would be a useful image into something that is complete garbage. So there are all sorts of other interesting things that you have to think about when designing a satellite to make sure that you actually end up with something that you want, that it's not wobbling, that it is taken of the right place on the ground. Okay, so that's enough about building satellites. What are they for? Why would I want to take one? Now, in the movies, it's a lot about video. You always see that the bad guy is escaping, and they call in and say, we need to get the satellite overhead, and they call the satellite in, and it nicely follows the bad guy while the hero comes to the rescue, and everything works out really nicely in the end. Unfortunately, it doesn't work quite like that in real life, at least at the moment. But video is a new thing that is becoming a lot more prevalent. This is actually a video that we took with one of our satellites in orbit just this year. this is Dubai. And those little dots you can see there are cars and vehicles moving on the motorway. Now, what the problem that we have with this is that, as we said, the satellite is flying at 7.5 kilometers per second. So whilst you can pitch the satellite to look at a particular point on the ground, and you can stare, maybe you can rotate the satellite as you're flying past, you don't get that long before the satellite has gone completely out of view, which means that the video that you're taking doesn't last for very long. So it's very nice while you look at it, and it does look quite cool, but it doesn't last for very long. Now, one of the interesting things about video at the moment, why video is becoming more interesting to people, is because as the satellites become cheaper and as the satellites become quicker to build, the possibility of having constellations of these satellites, and Matthew mentioned some fairly large constellations of satellites just now, is a lot more possible. So you could imagine now a situation where one satellite takes a video bit like this, and as it moves out of the view, another satellite comes in and picks up where it left off. And with enough satellites like that, you can start getting to the point where some kind of continuous coverage of a particular place might be possible. This is another video. This was taken by a Canadian company called Earthcast. They're doing some very interesting and exciting new things in the Earth observation world. This one, if I start it playing, is actually taken of a military base in the Middle East. Now, I'll leave you to the imagination as to why you might want to take that kind of video. But particularly interesting is that, and you can just about see a person walking between two buildings there. So if you compare that with what you see in the movies, this is kind of what you can do at the moment. I can't see the person's face. And also, you had to get really lucky to get that video. This wasn't a case of let's call the satellite in and take that video. The satellite happened to be flying past at that time. It was pre-programmed to take that video, and it just so happened to catch a person walking by. So, that's enough about video. Why should we want to take a picture? Why is it worth spending the millions of pounds that it costs to build a satellite, even more millions of pounds to launch that satellite into space, more millions of pounds to insure it, because if the rocket blows up, you probably want to get your money back, or millions of pounds to operate the satellite for the 10 years or so before it does then re-enter into the atmosphere and stop being useful? Well, I asked that question to my team a couple of years ago. I said, okay, for the next 13 weeks, I want one of you to research and present back on some kind of useful application of Earth observation. And that way, we're all going to learn some really good stuff about how we can convince our customers to buy these satellites. I should have known better. What I actually got was spotting penguin poo and watching algae grow, which wasn't kind of the revelation that I was looking for. But actually, they are real examples of what satellites are being used for. In this picture, you can see the dark patch in the middle is penguin poo. It's much easier for the satellites to see the mess that the penguins have left behind than it is to see the penguins themselves. And what scientists do is to use that so that once they have found where the penguin colonies are, using some kind of algorithms to pick out the number of penguins is a lot easier. And you can use that information then to track the populations of these penguin colonies and see how kind of climate change might be affecting their population size. Watching algae grow, well, yeah, watching algae grow, I think probably it came as a big disappointment that none of them could find an example of watching paint dry. And this was the closest they could manage. But again, it's actually something that is really being used. In this case, scientists will use the fact that the algae is growing to understand what that means about the nutrients that are being fed into the lake, and therefore what impact that's going to have on the local industry, whether it's fishery or tourism and so on. So what sounds like kind of fairly obscure applications are actually real-life things that people are doing all the time. Now, when most people think of Earth observation, they think of the images that you see on Google Earth. And whilst that is a lot of the kind of images that you can get from satellites, actually there's a much wider range of that. And it all comes down to the electromagnetic spectrum. So probably a lot of you are familiar with this. This shows the electromagnetic spectrum across the different wavelengths. And you can see there with the radio waves at one end, right the way through the visible to gamma rays on the outside. Now, what's interesting about this is that there are only actually two parts of this EM spectrum that penetrate the Earth's atmosphere. So if you're in space and you want to observe something on the ground, you have to be looking in one of the two areas that is possible. One is the radio waves, and the other one is the visible and just about into the infrared slightly. So that's where all of the Earth observation satellites are operating. The first one, then, in the visible and near infrared, this is what optical imaging is about. Now, optical imaging is a passive type of imaging. You are just relying on the signal that is coming from the sun. It bounces off the Earth. Of some of that light that is reflected off the Earth, it goes back up into space, and some of it ends up being captured by the satellite that's flying past. So this is a much easier type of Earth observation in the sense that the satellite is not having to do anything other than to pick up that signal. But it has its downsides. If it's cloudy, the light is blocked by the clouds, and all you actually end up with is an image of clouds, which is not that useful. Similarly, if it's dark, there is no signal at all, and the image that you would catch from the satellite is dark. But you do end up with nice-looking pictures that are easy to interpret. This is an image of London. This was taken by one of our satellites last year, and it looks the way that you expect it to look. It's easy to see what's going on, and it's generally a nice picture to look at. On the other hand, in the radio waves, we use a thing called synthetic aperture radar. And this is a satellite which generates the signal that it's actually going to pick up itself. So rather than working in the optical wavebands, it's working in the radio wavebands. It is generating a signal which it fires towards the Earth, and it's that reflected signal that comes back off the Earth that satellite is picking up. This has a number of different advantages. You can do it at nighttime. It doesn't matter what the sun is doing because the satellite is producing the signal, so it works just the same. And because radio waves penetrate things like clouds, you can also do it through clouds. So getting a radar image, whether it's in the day or the night or whatever the weather, is possible. Also, because of the way that radio waves do penetrate even more solid objects to a certain extent, you can use different kinds of radar satellites to image through the trees. Maybe you want to see what's going on at the bottom of a forest rather than what's reflecting off the top of the trees. Or maybe you want to see what's going on at the bottom of the ocean in the coastal areas, because some of these radio waves will penetrate a certain amount of the water. The downside of it is that the image doesn't look so nice. This is a radar image, and you can tell what's going on with it, but it doesn't look the way you expect images to look, and actually getting some real understanding from the image is a lot harder. This kind of image interpretation requires a lot more skill and experience from the people who are looking at it to get something useful out of it. The other downside to radar is that because you are generating the signal yourself, you require a huge amount of power on the spacecraft, whereas an optical satellite can make do with maybe the same kind of power as a light bulb in your kitchen to run the entire satellite. A radar satellite requires kilowatts of power, which means that it's a lot bigger, and it's a lot more expensive. Okay. So that's the difference there between optical and radar. Now, broadly speaking, there are two kinds of reasons why you might want to be taking an image of the Earth. The first is that there's something that you're looking at. You're actually just interested in the content of the image. And into that category, I put all sorts of things. There are military applications. You know, is the bridge still there? Before I send my troops across it, will they find a gaping hole at the other end? You know, what was the result of the last battle? Where are the fires raging? What needs to happen to send help in this situation? A topical example at the moment, the South China Sea. You may know that this is a fairly hotly contested region, with all of the neighboring countries interested in protecting their rights in the South China Sea. Well, the approach that China is taking is to build islands where there were no islands previously. This is actually an island called Fiery Cross Island. It started off life as a reef, and China decided to build a new port and airbase there. And you can see that over the course of a year, it's gone from something that was barely there, and even that's not right at the beginning, to a fully populated military establishment. And of course, the aim for them is to say, this is a region that now belongs to us, and we can protect it by force. Now, Earth observation doesn't stop them from doing that, of course, but it does at least tell everybody what's going on, so it doesn't come as a surprise. There's some more commercial applications. This is an image where people were interested in looking at how many trucks there were in a depot. Another similar example is how many cars are in the supermarket car park. Why would you care about how many cars are in the supermarket car park? Well, for people who care about these kind of things, looking at the number of cars in the supermarket will tell you how many people there are in the supermarket, and from that you can tell how much money the supermarket is likely to be making. And therefore, what is the share price of that supermarket going to do? Which means that I could now speculate that and make a lot of money for myself. So from a very simple image, a repeated image of the cars in a car park, I can start actually making some money. There are other also commercial applications. This is an oil field in Egypt. And what the analysts have done is they've looked at this, they've looked at the floating height of the tank on that the storage facility, and they've used that to establish what the supply of oil and gas is in that region. If you look at that across the entire globe, you start being able to understand what the supply of oil and gas is globally, and therefore what the petrol price is going to do. And of course, that's what drives the world's economy. So having that kind of information tells you a lot about what's going on in the world. This is a more humanitarian example. This is the border between Syria and Jordan. And what the satellite here was doing was looking for the shelters of all the refugees that are trying to get from Syria into Jordan. So this kind of information for aid agencies is really important for knowing where you should be going and what kind of size the problem is. This is an environmental example. This is the Amazon rainforest. This image was taken in 1986. If we fast forward 20 years, you can see that there are vast tracts of the forest which are no longer there. This is a slightly weird colored image in that the red is showing the forestry there. That's taken in the near infrared, which is slightly easier to pick out the vegetation. But all of that kind of turquoise color is now farmland. To put it in perspective, that area of that image is about 40,000 square miles. And this is just one small part of the Amazon where this kind of thing is happening. So if we then move out of the commercial applications, as EO becomes more mainstream, some of the individual applications might now be possible as well. So maybe I just want a picture of my house. Well, she's just there. There's got to be some benefits of having your own satellites to play with. Or maybe I want to see where I'm going to want to go on holiday. Actually, this is a picture of the Bahamas, and I thought, actually doesn't look quite the way I was expecting it. I was expecting more kind of sandy beaches, so maybe I don't want to go on their holiday after all. But you know, as Earth observation becomes more available, these kinds of things become more possible. So I'm going to now move into the other area of why you would want to be taking image, which is a bit more scientific. All of the examples that we've just looked at there were about content. It didn't matter what the values that were being used were. The other reason is much more scientific, where you care about what the pixel value is. Why should I care that the value of this pixel is 42 as opposed to 197? And just as one example of this, this is something called precision agriculture. So if a farmer can understand exactly what's going on in his field, then rather than watering the field uniformly or applying pesticides uniformly across the field, he can start to make some decisions about, well, I'm just going to water the bits that need it, or I'm just going to apply pesticides in the bits that need it. But to be able to do that, you have to understand very accurately what's going on in the bits of the field. To do that, they can use imaging satellites that are specifically designed to look at the chlorophyll response. So chlorophyll is a pigment that's found in plants and algae, and exactly what you find is that healthy plants, because they absorb more chlorophyll, look less red. They have absorbed more of the red light. So when a satellite is looking at it, it will look less red. So I can then take two curves. This shows what a response from a healthy crop and an unhealthy crop looks like. And I use a very simple equation to work out an index for what that crop health might be. I thought I'd only do one equation, so I've left it till the last. But that's what the equation is, and quite simply, I take the value of the red and the value of the near infrared, and I can work out a value for what that crop is, what the health of that crop is. If I then do the same for the unhealthy crop, I get a comparison. And these kinds of things are very useful for allowing the farmers to make decisions as to the kinds of things they should be doing with their crops. So I'm conscious that I'm running out of time here. So I hope that I've given you a kind of flavor that Earth observation is more about pretty pictures. I think there are a lot of things coming. I think we're probably at the verge of a bit of a revolution in Earth observation. Only recently, really, has commercial Earth observation been possible. Before then, it was really only government-backed Earth observation that was being done. But I think before long, we're going to find that we're in a position where individual Earth observation is a lot more possible. Very soon, we're going to be having satellites that will take a map of the world every single day. It won't be long before you can do continuous video coverage of areas on the ground. And it also won't be long before you'll be able to go onto your phone and say, you can have a picture of where I'm standing right now, and shortly afterwards it will arrive on your phone. So, exciting times, but there are also pretty pictures. Thanks.
Thank you, Andrew. Do we have a couple of quick questions for Andrew? I saw a hand go up over there.
Yeah, a couple really. Firstly, how accessible is the information from these satellites? And is there any distinction between what's happening now in the commercial space and the previous government-owned observation satellites?
So how accessible, it depends really. I mean, there are a lot of satellites up there doing this kind of Earth observation. The European Space Agency has a program called Copernicus, which is all about making the imagery from their satellites available. And that imagery is available for people to log on and to use for the various applications that they have. Obviously, the commercial satellites, the reason for having the imagery is for those commercial companies that operate them to sell. So that kind of imagery you can buy commercially quite easily, but it costs money, of course. So there are different ways of getting the imagery. It really depends on what you're trying to do with it and what, other factors like how quickly you want it and so on.
And with that, are there any censorship issues, sensitive areas, nuclear power plants, military establishments, people being able to access that information?
So imagery is subject to export controls in the same way that a lot of technologies are. So it's up to the governments that license the satellites in whichever country they are licensed in to determine the rules. So it may be that providing imagery to North Korea, for example, is more restricted than providing it to a company that's based in the UK. But that's up for the local licensing authorities to determine.
This one over there, I think.
With current technology, what's the sort of maximum or minimum size object that these satellites can get without giving any state secrets?
Well, the kind of best resolution that is currently available is about 30 centimeters. Just recently in the US, they've changed the laws about the best resolution that can be made publicly available, and they've reduced that to 30 centimeters. It was previously at 50 centimeters. It's not much beyond that before you start running into the limits of physics, that it's not possible just to get better than that. But that's kind of where we are at the moment.
One more, perhaps.
All the things you showed were pretty impressive, but one thing that was distinctly surprising and underwhelming were the images of the Middle Eastern base, and you could see the little moving pixel that you said is a person. And I think most of us live under the perception that we are totally visible, from space. You look up and the government can see you.
Yeah.
Is this one area where we're sort of misinformed in the other direction? We're a bit
Absolutely. This is what Hollywood has done for us. You can't. If you can't believe what you see in the films, not at the moment anyway. This kind of idea of being able to zoom in and pick out a person's face and watch them as they run around is not possible at the moment. That kind of video really is, where you could just about see that there was a person there, is kind of what's possible, rather than that detail that you kind of are led to believe is possible from films.
Can I suggest that if you have any further questions for Andrew, you catch him at the lunch break, which will be in about half an hour. But just before we go into the final session before lunch, can I ask everybody to thank Andrew again?